This is a little bit of story time, okay? If you're going into the realm of deep learning and you're going to be more than superficial, if you're really going to get deeper into the mathematics, then what you're going to find is that it's like studying alchemy, okay? This is like solving an Illuminati code in a Dan Brown novel. If you followed Dan Brown's novels, you know that his hero, Robert Langdon, teaches symbology at Harvard, and so he has all the requisite background to solve these complex, art history-dependent Illuminati questions. Do we have that? For almost everybody coming into the field, we don't have that requisite background. Now, I'm an exception, okay? I'm lucky. My daddy was a physical chemist. That is the sort of chemistry that does lots and lots of equations. And I'm my father's daughter. I grew up and became a physical chemist. Lots and lots and lots of equations. Lots of equations, okay? Whether this is a streak of blind good fortune or karmic brilliance, I don't know. But I'm in a really good position to teach myself the underpinnings of advanced AI. Even with all of that going for me, it hasn't been easy. So for somebody who's coming into the field like you, strong, smart, determined, willing to put in the time, but you're coming into this and you read the papers, or you try to read them, and the language is just not accessible. There's reference to the things that you can't understand. You try to research them on the Wikipedia, blogs, technical articles of all sorts, and it just piles up and it becomes impossible. And I get it. I mean, I'm having to struggle my way through a lot of this too. So what our goal is to find the elements of, regrettably, my dear, statistical physics, specifically statistical mechanics, which is a branch, a very arcane little branch of theoretical physics. We're going to find those elements that you absolutely need, because I know you do not have the time to go and, take a couple of years off your life and get a PhD in theoretical physics. Nobody does, really, I know that. So what we're going to do over time, you and me, that's why we're having this little vid series, this is why I'm writing the book, is we're going to get you just what you need. We're limiting it to that which you absolutely need to get through and to be able to approach those papers, those classics, with that, with the bare bones, necessary, minimalist approach to statistical mechanics. You'll be able to get through some of those classics, but it's more than that, and this is the kicker, okay? This is why we're having a break from my just jumping into the slide deck and, next round of equations. We're having a private little conversation here. And it's that there's more than just the statistical physics involved. There's the whole aspect of probability theory, and combining the two together is where we hit that Illuminati moment. It's alchemy. It's living in two realities at once, because frankly, the notion of probability as it pertains to Bayesian probabilities and the notion of probability as it pertains to statistical physics, those two realities do not coexist, okay? And if you're at all going deeper into the equations and not just sort of blithely following through, you have this moment where you say, oh my God, what are we really doing here? These two equations should not exist in the same formalism or in the same worldview. And yet they do. And it's actually the heart and soul of where the advanced machine learning algorithms are moving. So we kind of have to accept that. We have to have this alchemical understanding, and we have to be able to work with the fusion of two very, very different notions and then follow the logic forward. This is not a simple thing. And both of those realms require a fair degree of pre-study. In particular, to do the statistical physics thing, you need three things, already. We can boil it down to three. You need free energy. because all of the world in machine learning and deep learning and advanced AI depends on free energy. Free energy is a physics concept, okay? It's not like, you can turn on a faucet and get energy for free, or you can look at your bill and say, wow, I got all this energy for free. No, it's a theoretical mathematical construct in physics. To do free energy, you need two terms. One is enthalpy, which is an energy term, and the other is entropy. And you probably have dealt a lot with entropy and you've seen it. A weird thing will have happened in your education, though. People will have presented the notion of entropy to you as a singular, isolated concept, whereas in the reality of things, entropy always coexists with enthalpy, and the two come together and contribute to free energy. We're going to have a long discussion about that. It's coming up. I'm just saying that you need that. Now, before you can get to the free energy with the enthalpy and entropy, you need the partition function. That's the starting function from which you get your free energy. To get the partition function, you need microstates. So it's a cascade of things to learn. Microstates, partition function, free energy, and then you've got to learn how free energy can be viewed two different ways. One is as a expression of the partition function, and the other is a combination of enthalpy and entropy. Do that, and you're solid. It's a lot of work, but you're solid. Then you want to go off and put on a totally different mindset and study Bayesian probabilities. You want to be able to feel very fluid and comfortable and familiar with the notions of covariating or the a posteriori, that kind of thing. So that as we play with those equations and we say, oh, it's hard to get this, it's computationally intractable, but you can do that, you're not weirded out. You're flowing with that conversation. Once we get these two entirely different schools of thoughts together, we can pull them together and start in on the machine learning. The first thing that we're going to do is look at the Kullbeck-Leibler divergence. I'm sketching the overall here. Kullbeck-Leibler divergence, which on its own is not that horrifying a thing. It's a measure, and we can look at it and it's not at all difficult. What happens, though, is that they take extreme and severe and weird liberties with the Kullbeck-Leibler. Let's call it KL, okay? They take liberties and start to finesse it, and some of the things that happen look a lot like a free energy equation, and that winds up being important, and that's why we need to study the whole physics end of things. So that's where we start seeing that combination of probabilities that are coming from a Bayesian perspective together with statistical mechanics. We do that, and then we can start looking, I know this is a long path, but it's kind of like our trek through the mountains. It's sketching our journey. We do that, and we can start to look at the NLP algorithms. And then we're starting to look at things like latent Dirichlet allocation, LDA. We're beginning to look at word-to-vec and doc-to-vec, and then we're also positioned to look at BERT, the bidirectional encoder algorithm. Alrighty. Does this sketch out half a year to a year of work? I'm afraid so. But thank you, and join me in the next vid, and we'll be moving forward. Till soon.